What if the defining moment of our entire universe, the Big Bang, is basically just based on a mathematical illusion?
Of complete illusion, yeah. It's a pretty wild thought.
Right. I mean, I want you to picture the standard story we've all been taught in science class. You strip away the Earth, the sun, all the galaxies, and you run the clock backward 13.8 billion years until everything that exists is crushed into this single, infinitely dense, infinitely hot point, the singularity.
The famous singularity?
Exactly. It's supposed to be this dramatic starting gun of existence, but physicists have a dirty little secret about that point of infinite
They
density.
really do.
They don't actually believe it exists. So welcome to the deep dive. Today we are taking you to the absolute edge of cosmic history.
Yeah, the very edge.
We're going to look at a breakthrough that suggests the universe never actually started with a singularity at all.
It is arguably the most profound mystery in modern cosmology today. Because that singularity, it's not a physical object we can just observe through a telescope.
Right.
It is essentially a glitch. A massive, glaring glitch in our best models of reality.
A bug in the cosmic code.
Exactly. For decades, it has stood there as this impenetrable wall, basically mocking our attempts to understand how time and space actually began.
And the reason we are finally peering over that wall today is a really groundbreaking paper. It was published in May 2026 in the journal Physical Review Letters.
Quite a prestigious journal, yeah.
Yeah. And the mission of this deep dive is to explore this new framework coming out of the University of Waterloo and the Perimeter Institute.
The ideas they put forward are just phenomenal.
They really are. It's a subtle but brilliant tweak to our understanding of gravity itself. And this tweak doesn't just, erase the singularity.
No, it goes much further than that.
Right, it completely rewrites the opening chapter of the cosmos. It drops the need for all these hypothetical sort of magical ingredients that physicists have been using to patch their models for years.
They've been using duct tape for a long time.
Oh, absolutely. So, okay, let's unpack this. Before we can really appreciate the mechanics of this new breakthrough, we have to look at the engine that is currently failing us.
We have to talk about Albert Einstein.
Yes, we have to talk about Einstein's general relativity.
General relativity is, it is the undisputed heavyweight champion of macroscopic physics.
Without a doubt.
Einstein taught us that gravity isn't some invisible tether just pulling planets together like magnets. Space and time form a physical fabric, right? A four-dimensional grid.
Like a trampoline, basically.
Exactly like a trampoline. When you drop a massive object, like a star, onto that fabric, it sags, it curves.
And things roll down toward it.
Right. That curvature dictates how other objects, and even light itself, move through the universe.
And we see the proof of this everywhere. General relativity predicts the exact orbits of the planets.
It explains how massive galaxies act as magnifying glasses, bending the light of stars behind them.
Yeah, and it's the reason the GPS satellites communicating with your phone right now can actually pinpoint your location. The math is an absolute masterpiece.
It really is beautiful.
But the engine has a catastrophic breaking point. Actually, it has two breaking points.
Two very distinct places where it falls apart.
Right. It shatters inside the hearts of black holes, and it completely self-destructs at the moment of the Big Bang.
Because when you apply the equations of general relativity to the early universe, you are taking all the mass and energy of 100 billion galaxies.
Which is mind-boggling to even think about.
It is, and you're compressing all of that into a space smaller than an atom. The equations show the fabric of space-time curving more and more intensely.
Just warping beyond belief.
Exactly. The temperature skyrockets, the density climbs, and eventually the math just gives up. The variables hit infinity.
I always picture general relativity like a beautifully engineered race car engine.
Oh, that's a great way to look at it.
Right. If you are cruising on a track, it purrs. You can calculate fuel efficiency, speed, friction, all of it perfectly.
It does exactly what it's built to do.
But if you put that car in neutral and just jam a brick on the accelerator, pushing the RPMs toward infinity, the engine doesn't just spin forever.
No, it would explode.
Exactly. The heat melts the block, the pistons shatter, the physical structure literally blows itself apart. The machine just cannot handle the absolute extreme.
What's fascinating here is that the theory is pushed entirely out of its domain of applicability. General relativity was engineered to describe a universe that is, relatively vast and relatively cool.
Sure. Normal conditions, basically.
It simply does not possess the mathematical vocabulary to describe a universe squeezed into a subatomic space.
So let me stop and push back on this for a second, because I know you listening might be wondering the exact same thing right now.
Go for it.
If the math of general relativity spits out an infinity for temperature and density at the Big Bang, isn't that just nature's way of giving us a giant error 404, physics not found message?
That is exactly what it is.
And if that singularity is just a math error, what does that mean for black holes? I mean, we literally have telescope photos of black holes. Are you saying we're just wrong about them too?
That is the perfect question to really expose the heart of this problem.
Okay, lay it on me.
When we look at those incredible telescope images of black holes, what we are actually seeing is the event horizon. That's the outer boundary where light can no longer escape.
Right, the shadow part.
Exactly.
Yeah.
That boundary is very real, and general relativity predicts it perfectly.
Yeah.
But the singularity inside the black hole,
The point at the very center where all that swallowed matter supposedly compresses into a single infinite dot.
yeah, that dot. Most theoretical physicists will tell you that doesn't physically exist either.
Wow. So the engine shattered there too.
Exactly where gravity becomes unimaginably extreme. And infinity in a physics equation is basically nature's neon sign flashing, "You are missing a piece of the puzzle."
It's saying, hey, look over here, you messed up.
Right. It means that the theory has lost its grip on reality. And we have been staring at that error 404 message for almost a century now, desperately trying to build a better engine.
We need a framework that can handle those extreme primordial energies without producing those fatal infinities.
Precisely.
Which brings us to the physicists at the University of Waterloo and the Perimeter Institute.
The new mechanics, so to speak.
Yes, they are the mechanics proposing an entirely new set of parts for Einstein's engine, and they call their extension quantum quadratic gravity, or gravité quadratique quantique if we're being international.
It sounds incredibly dense, I know.
Yeah, it's a mouthful.
But the core philosophy is actually highly intuitive. They aren't throwing away general relativity. Einstein's theories are still the absolute foundation.
So they aren't starting from scratch.
Not at all.
Yeah.
But they are adding new mathematical terms to the equations, specifically terms that are squared, which is where the quadratic part of the name comes from.
Okay, here's where my brain gets stuck, and we definitely need to clarify this for everyone listening.
Sure, what's the sticking point?
If the problem with general relativity is that the numbers get too big and shoot off to infinity, how on earth does squaring the variables help?
It sounds like it would make it worse, right?
Yeah. If I have a massive number and I square it, I just get a massively larger number. Adding quadratic terms sounds like throwing gasoline on an engine fire. How does this fix the infinity problem?
It totally seems counterintuitive until we look at what specific terms are actually being squared. They aren't just squaring the density or the mass.
Okay, what are they squaring then?
They are adding squared terms related to the curvature of spacetime itself.
Ah, the curvature.
Right. In standard general relativity, the mathematical terms dictating gravity are linear. As matter compresses, the gravitational pull gets stronger in a very straightforward compounding way.
It just pulls harder and harder the smaller things get.
Exactly. But under quantum quadratic gravity, the new squared curvature terms come with a crucial mathematical feature. They have the opposite sign.
Wait, the opposite sign, like negative instead of positive.
Yes. They act counter to the standard pull of gravity. In our everyday world, or even near a star, the curvature of space is relatively gentle, so these squared terms are just microscopic.
They are effectively dormant. You don't even notice them.
Exactly. So the engine runs like normal on the highway.
Okay, but what happens when things get extreme?
Well, when you crush the universe down to quantum scales, the curvature of spacetime becomes incredibly violent. Suddenly, those squared terms wake up.
Because they're squared, so they get big really fast.
Bingo. They scale up exponentially, much faster than standard gravity. And because they have that opposite sign, they essentially act as an immense repulsive force. They act as a built-in shock absorber.
Wait, so as the universe gets crushed smaller and smaller, gravity stops pulling and starts, resisting.
Think of compressing a massive, heavy-duty steel spring.
Right.
At first, you can squeeze it together pretty easily. The standard laws of gravity are pulling the coils inward. But the tighter you compress that spring, the more fiercely the metal itself fights back.
It pushes out against your hands.
Exactly. Eventually, you hit a point where no amount of force can compress it any further. The internal resistance matches the outward pressure perfectly.
The mathematical shock absorbers deploy.
And the math smooths out completely. By treating gravity this way at extreme quantum limits, the density never reaches infinity. The temperature never reaches infinity.
So it stops before it breaks.
Right. The universe compresses down into an unimaginably hot, dense state, sure, but it is a finite state. It still obeys the laws of physics. The singularity is completely eradicated.
Wow. That is a staggering achievement. I mean, removing the singularity is basically the holy grail of early universe cosmology.
It's what everyone has been trying to do for decades.
But a good scientific theory cannot just, fix a math error. It actually has to explain the universe we see around us today.
It has to match reality.
Exactly. And the Waterloo team's framework yielded an entirely unexpected bonus here. It solved a second massive mystery without even trying.
And that is the hallmark of a truly profound breakthrough. When it elegantly solves adjacent problems you weren't even actively targeting, you know you're onto something big.
To really understand this bonus, we need to look at what happened immediately after the beginning.
The first fractions of a second.
Right. For you listening, the accepted theory for the first fraction of a second of our universe is called primordial inflation.
It's a very dramatic period.
Yeah, the universe didn't just expand at a steady, leisurely pace like a balloon being blown up. It underwent a violent, exponential growth spurt.
Faster than the speed of light.
Yeah, it stretched from a microscopic speck to macroscopic size in less than a blink of an eye.
And we know this massive growth spurt had to happen because of how strangely uniform the universe is today.
Right, the temperature is too even.
Exactly. When telescopes look out at the deep cosmos, the temperature of the background vacuum is almost perfectly identical in every direction.
No matter where you look.
Right. Regions of space that are currently billions of light years apart, on opposite ends of the observable universe, they have the exact same temperature down to fractions of a degree.
Which shouldn't be possible unless they were once right next to each other, sharing heat, before being violently ripped apart.
The only way to get a universe this smooth and uniform is if a tiny, thoroughly mixed patch of space suddenly inflated to an enormous size.
The problem with the classical models of the Big Bang was that physicists had no idea why this inflation happened.
No mechanism for it at all.
Right. General relativity couldn't explain it. Standard gravity only pulls things together. It definitely doesn't cause space to suddenly balloon outward.
So they had to improvise.
Yeah, decades ago, theoretical physicists basically used duct tape to fix their model. They invented a hypothetical energy field and called it the inflaton field.
And the inflaton field has always been a major point of contention. It was literally a mathematical placeholder. Yeah, physicists had to manually insert this imaginary field into their equations and fine-tune all the variables to incredibly precise, totally arbitrary numbers, just to make the math match what telescopes were seeing.
It honestly felt a bit like cheating.
It really did.
Yeah.
You had standard physics, and then you had this mysterious, invisible force that just conveniently switched on, caused inflation, and then switched off forever.
Here's where it gets really interesting. Reading through the historical context of the inflaton field in the source material, it reminded me of cooking.
Okay, I like a good cooking analogy.
So if you are baking a loaf of bread, you have your flour, your water, and your salt. That's standard general relativity.
The basic ingredients.
Right. But if you want the dough to rise aggressively, you have to rip open a completely separate packet of yeast and dump it into the bowl.
Ah, I see where you're going with this.
The yeast isn't a natural property of the flour. It is an external ingredient you are forced to import. The inflaton field was the yeast.
That's a great way to put it.
But the Waterloo team realized that under quantum quadratic gravity, you don't need yeast. In fact, baking is the wrong analogy altogether. It's more like a pressure cooker.
A pressure cooker is a much better way to visualize the mechanics here.
Right, because if you put water in a pressure cooker and subject it to extreme heat and pressure, you don't need to add a magical steamifying chemical to make it expand.
No extra packets required.
Exactly. When it hits a critical threshold, the fundamental state of the water changes. It flash boils into steam, expanding violently all on its own. The capacity for that extreme expansion is built directly into the physics of the water.
That captures the beauty of their findings perfectly. Once the researchers applied the coherent mathematical framework of quantum quadratic gravity, they realized they didn't need to artificially inject an inflaton field.
It just happened.
Right. The phase of rapid exponential expansion emerged entirely naturally from the equations.
Because of the shock absorbers.
Because of the shock absorbers. When the universe was at that incredibly dense primordial state, those squared curvature terms were dominating.
The stiff spring fighting back.
Yes. The extreme gravitational resistance, that stiff steel spring pushing back, didn't just stop the collapse. That immense repulsive gravitational pressure actually drove the inflation.
Wow.
Gravity itself provoked the universe to balloon outward.
The force we usually associate with pulling things together became the very engine of expansion. That is wild.
It is. The early universe didn't require extra ingredients or highly tuned hypothetical fields. Gravity inherently possesses the mechanics to both prevent a singularity and trigger inflation.
Provided we understand how it behaves at the quantum limit.
Exactly.
You know, the researchers used a fascinating visual metaphor to describe this self-driven
The
expansion.
cosmic web.
Yeah, they described the fabric of early spacetime like a cosmic web made of highly energetic, interconnected nodes. In the old classical models with the inflaton field, you'd have to imagine some invisible, ghostly hand grabbing that web and aggressively stretching it out.
Just yanking it apart.
Right. But under this new framework, the intense quantum energy pulsing inside the nodes themselves forces the grid to expand. Space-time inherently wants to stretch when subjected to those extreme quadratic forces.
It creates a universe that is entirely self-contained. It follows its own natural internal logic from the very first moment without needing ad hoc external forces.
It is incredibly elegant, but, as beautiful as this pressure cooker mechanism is, a whiteboard full of elegant math is still just theory.
True. Science needs proof.
Right. And for you listening, we are talking about proving a microscopic event that happened 13.8 billion years ago. We can't exactly build a time machine.
Sadly, no.
So how do you dust for fingerprints at a crime scene when the room itself has been expanding for 14 billion years? How do these scientists actually plan to test quantum quadratic gravity against reality?
It is the ultimate forensic challenge, really. We obviously cannot observe the birth of the universe in real time, but the violent events of the early cosmos left behind incredibly subtle physical fossils.
Fossils in space.
Yes. And the researchers laid out concrete pathways for testing their theory using two specific cosmic relics: primordial gravitational waves and the cosmic microwave background.
Okay, let's break those down for everyone. Gravitational waves are literal ripples in the fabric of space-time, right? Like throwing a rock into a pond.
That's a perfect analogy.
So when the universe underwent that violent, rapid inflation, the massive shifting of energy basically rang the fabric of space like a giant bell.
And those ripples have been traveling outward through the universe ever since. They're stretching and fading, obviously, but they are still washing over the Earth today.
And what about the second fossil?
The second fossil is the cosmic microwave background, or CMB. It is essentially the visual afterglow of the Big Bang.
The oldest light in the universe.
Exactly. About 380,000 years after the initial expansion, the universe finally cooled down enough for the first atoms to form, which allowed light to travel freely for the very first time.
And we can actually see that light today. When telescopes map the CMB, it looks like an oval globe covered in tiny red, blue, and yellow speckles.
It's a map of the universe's oldest static.
Yeah. And those different colors represent microscopic temperature variations, literally fractions of a degree in difference.
And those tiny temperature variations are incredibly important. They aren't just random static. They are the macroscopic shadows of subatomic quantum fluctuations that existed during inflation.
So when the universe expanded faster than light, it took those microscopic quantum jitters and stretched them across the entire sky.
Precisely.
So how does mapping those temperature speckles prove quantum quadratic gravity?
Because different engines leave different exhaust signatures.
Okay.
The old classical models of inflation, the ones relying on the artificial inflaton field, predict a very specific distribution of those hot and cold spots. They predict a certain ratio of large speckles to small speckles.
And the new model?
Quantum quadratic gravity, because it relies on the repulsive force of space-time curvature, predicts a slightly different structural motif.
It leaves a totally different fingerprint in the static.
Furthermore, the signature in the primordial gravitational waves is also distinct. The way space-time rings under quadratic gravity differs mathematically from how it rings under an artificial energy field.
So we just have to look at the data.
And the researchers have demonstrated that the model obtained from quantum quadratic gravity already aligns remarkably well with the CMB data we currently possess from satellites like Planck.
But the current maps aren't high resolution enough to declare a definitive winner yet, right?
Right. The current data is fantastic, but we need unprecedented precision to differentiate between the subtle nuances of these two models.
We need better cameras.
Essentially, yes. That is why the next generation of space observatories, like the Lightbird satellite and various ground-based CMB experiments, are so critical.
They are looking for the exact signatures.
They are being engineered specifically to measure the polarization of the CMB and the faint hum of those ancient gravitational waves with a sensitivity we've never achieved before.
So the team at Waterloo has basically laid down a highly specific, falsifiable prediction. They've said, when we turn on the new cameras, the ancient light is going to look exactly like this.
If we connect this to the bigger picture, if future observations detect the precise structural motifs predicted by quantum quadratic gravity, it will be a monumental confirmation.
A total paradigm shift.
It would definitively sideline the classical inflaton models, prove that Einstein's engine just needed a quantum extension, and confirm that we finally understand the physical mechanism that burst the cosmos.
So what does this all mean? Let's zoom out and give you listening the grand takeaway from this deep dive into the May 2026 breakthrough.
It's a lot to process, for sure.
It is. For generations, the textbook story of the universe has forced us to accept an impossible broken dot, a singularity of infinite density where all the laws of physics simply collapsed.
The Error 404 message.
Right. And to explain how we got from that broken dot to the vast cosmos, physicists had to invent a magical invisible field to forcefully stretch space apart.
The yeast in the bread.
Exactly. But quantum quadratic gravity offers a profoundly elegant alternative. By acknowledging that space-time curvature has a built-in mathematical shock absorber at extreme microscopic scales, the infinite point vanishes.
It just disappears.
The engine doesn't explode, it just hits maximum resistance. And that immense quantum-level resistance naturally triggers the explosive expansion of the early universe. The cosmos didn't need extra ingredients. Gravity itself was the ultimate engine of creation.
It strips away the magical thinking and replaces it with a universe that is beautifully self-sufficient.
This is just brilliant.
But, it leaves us with a jarring paradox that fundamentally challenges how we view the physical world.
Oh, what kind of paradox?
Well, consider your everyday experience of gravity. Right now, it is the force anchoring you to your chair.
Keeping my coffee on the desk.
Exactly. It is the invisible glue binding the Earth to the sun, holding galaxies together, pulling matter inward. We define gravity by its relentless attraction.
It is the ultimate pull.
Yet, if this framework is accurate, the very first act gravity ever performed was the exact opposite.
Wait.
In the unimaginable heat and density of the first moment, gravity wasn't the cosmic glue. It was the ultimate cosmic repellent.
Whoa.
It was the explosive force responsible for violently pushing the universe apart.
It pushed before it pulled.
Exactly. So, here is a final thought for you to mull over long after this deep dive ends.
I love these.
If the fundamental force that holds our current reality together was actually born as a force of unimaginable repulsion, what happens if the universe ever compresses again?
Oh, man.
If gravity is capable of violently pushing everything apart at the extreme quantum limit, how might that change the way we view the ultimate fate and perhaps the rebirth of the entire cosmos?
That completely twists my brain in the best way possible. Thank you for walking through that with me.
It was a pleasure.
And to you listening, thank you for joining us on this deep dive. Keep questioning the universe, keep looking up, and remember that sometimes the most stubborn mysteries are just waiting for us to look at the math from a slightly different angle. We'll catch you on the next deep dive.